It's fair to say that the increased use of AFDDs in Amendment 2 to the 18th edition of BS7671 was one of the more controversial and hotly debated subjects of the last few years, certainly in electrical circles. To try and cut through the opinion and speculation and help us to understand what an AFDD is, does and doesn't do, we created a free training package to help you with your CPD. This is the video from that training package that we've decided to release to our wider audience. We really hope that it helps your understanding of this subject, and if you'd like to complete the course and receive an accredited certificate to count towards your annual CPD, then please click the link in the description to take you to the relevant webpage. We'll be considering the following subjects. What does an AFDD protect against? How does an AFDD work? What's inside an AFDD, and what does BS7671 say about AFDDs? So watch this video and then successfully complete the multiple choice questions and you'll automatically be sent a CPD UK certificate to verify that you've updated your knowledge. So what does an AFDD do? Well, to answer that, we need to understand circuit protection and the types of faults that can occur within circuits in general. So let's have a very brief side quest into the history of circuit protection. There are two big hazards associated with electricity. One is it can hurt and even kill people, and the other is that it causes heat, which can lead to fires. In fact, this second hazard is what really led to the wiring regulations coming into existence. They were brought about at the insistence of insurance companies who were sick of paying out for building fires caused by unregulated and dodgy installations. The problem with excessive heat occurs when too much current passes through a conductor. This causes the conductor to get so hot that it can start a fire. What causes too much current to flow? It can be one of two things. The first is when too many loads are connected to the circuit, causing it to literally overload, which is the name we give to this kind of fault. The excess current in this case is likely to be relatively small but can still cause damage. The other reason too much current could flow through the circuit is if a line conductor comes into direct contact with another conductor, either another line conductor if it's a three-phase circuit, or the neutral or the CPC. This is referred to as a fault of negligible impedance, which kind of means very, very low resistance. And because it has a very low value of resistance, Ohm's law shows us the current flow in this circumstance would be huge, again leading to overheating and possibly starting a fire. To prevent this from happening, we provide overcurrent protection. This used to be in the form of a fuse, which was like inserting a weak link into a chain, in that a thin filament of copper inside the fuse would melt when too much current flowed through it, thus disconnecting the circuit. Over time, this was superseded by the circuit breaker, which had a mechanically operated disconnection system and had the advantage of being quick and easy to reset after it had tripped. The other hazard we want to mitigate against is people coming into contact with the electricity and receiving a shock. The simple way we do this is by covering the conductors in insulation to stop people touching them. There's other ways we do this as well, however sometimes these preventative measures can fail and someone can receive a shock. Most of the time this occurs to earth. When this happens, a fuse or a circuit breaker won't even notice it. This is because the path the electricity takes through a person's body has quite a high value of resistance, which means a relatively small amount of current. Nowhere near enough to trip a circuit breaker or a fuse, but more than enough to kill. So to prevent this from happening, we install a residual current device, or RCD. This monitors the current flowing through the line and back down the neutral, and if there's a difference in the amount of current between the two conductors, the device assumes that current is flowing through something it shouldn't, either the CPC or a person, and disconnects, potentially saving the individual. However, there is one more kind of fault that has become increasingly common, and that is the arc fault. These are generally caused when connections work loose over time and the connection between the conductors becomes tenuous. If the current flowing into the circuit is high enough, it can jump this small gap in the form of an arc. This situation can then be intensified by the arc carbonising the PVC insulation around the conductor, which can then start to generate some serious heat. In tests at the Lewden factory, the carbon rod used to simulate the PVC insulation reached 200 degrees Celsius, and it's not unheard of for arc faults to generate temperatures of 6,000 degrees Celsius. As you can imagine, this could very easily lead us to a situation where this could start a fire, leading to very dangerous consequences. But surely our fuse, circuit breaker or RCD will detect and disconnect this? Well, unfortunately not. The fuse or circuit breaker will operate when too much current flows, but in the event of an arc fault, there isn't an excessive amount of current flowing. It can be a relatively small amount, but the danger now arises from the arc causing damage not heat caused by the current in the conductor. What about the RCD? Surely that will see the fault and trip? Well, again, no. When an arc fault occurs, the current causing the arc is still passing down the line and back through the neutral, and so the RCD won't see a difference in the currents through those conductors, and therefore it won't trip. So in order to disconnect an arc fault, we need a new form of protection. Enter the arc fault detection device, or AFDD. We'll explain in a bit more detail how they work a little later, but let's stick with the subject of faults for now, as there are two different types of arc fault. These are series and parallel arc faults. The series arc is the one we've already discussed, where conductors don't make a brilliant connection with each other when they should. So let's say the line conductor in a circuit feeding an electric shower isn't brilliantly terminated into the isolator. The current may continue to pass through the connection and jump the small gap caused by the loose wire, then continue down the outgoing conductor to the load. Because the current continues down the same conductor, this is what's known as a series arc, or sometimes you may hear it referred to as a serial arc. Much like a series connected load, the current has to pass through the fault to reach the load. Now, a parallel arc is a little bit different. It's a bit like a short circuit in that the current passes from the line to the neutral without going through the load, and it can happen when the insulation surrounding a conductor has broken down or been damaged, perhaps by mice or rats chewing on it. Now, this may sound exactly like a short circuit, but it's a little different because the connection between the two conductors in this case is quite tenuous and intermittent. So the fault won't generate enough current to operate the MCB or fuse, but because it's tenuous and intermittent, it will create arcs, which can then cause an excess of heat and start a fire. So an AFDD will protect against both series and parallel arc fault. However, there is one exception to this, which is very relevant considering what BS7671 says about the use of AFDDs, as we'll see. This exception for protection relates to ring final circuits. When a circuit is wired as a ring, an AFDD will still be able to detect and protect against a parallel fault, but it won't be able to detect a series fault. This is because in a ring final circuit, the current has two paths that it can travel down. So if a situation occurs that could cause an arc fault, such as a high resistance joint, then the current that could potentially cause the arc and cause the device to operate will simply take the alternate low resistance path back to the board and not cause the device to trip. Of course, in that circumstance, you've still got the problems inherent with an incomplete ring final circuit. Maybe one more sign that they're on the way out. However, it's really important to note that in this event, an AFDD connected to a ring final circuit will continue to provide the other forms of protection that it offers, including overcurrent, overvoltage, and parallel arc faults. More on these in a moment. As well as this, the AFDD will also detect a serial arc in the lead of a load that's been plugged into the socket outlet of a ring final circuit, whether that ring is complete or incomplete. So it's not just the fixed wiring of the circuit that's protected against arc faults, but also the leads and loads connected to the circuit as well. So if an arc fault won't draw excessive current or leak it to earth, then how exactly does the AFDD spot these faults? Well, it's all down to monitoring the shape of the current waveform that the arc creates while it's occurring. We're used to thinking of a healthy AC supply of current looking something like this, with the current rising and falling predictably and evenly. However, in reality, it's actually a lot messier, even in a relatively healthy circuit, and in a circuit experiencing an arc fault, it's likely to look more like this. And that is how an AFDD detects an arc fault occurring. It's programmed to monitor the shape of the current waveform supplying the circuit, and then trigger the disconnecting mechanism when it sees characteristics like this. Now, if we take a look inside an AFDD, we can see the components that allow this to happen. It takes protective devices to the next level by incorporating a small PCB that's been programmed to monitor and recognize those waveforms we just discussed. This then features a triggering circuit that operates the tripping mechanism and disconnects the circuit. However, as electricians, we know that electricity can create sparks, even in healthy equipment operating totally normally. For example, common household items that use motors such as drills or hairdryers will often produce sparks during normal operation. It's simply caused by the connection between the carbon brushes and the contacts on the motor. When the motor spins, it can bounce the carbon brushes back a bit on their springs so that there's some moments of disconnection and reconnection. So, is there a risk that these sparks could fool the AFDD into thinking there's a fault and disconnecting a healthy circuit? Well, no, because again, this normal operation of a motor will produce its own distinctive waveform of current, and the PCB in the AFDD is able to recognize that as a normal healthy function and not cause it to trip. The way you think of it is that those sparks you see in the back of a motor are generally just that, a spark, not an arc. So you can imagine that this is slightly more technologically advanced than a simple fuse, MCB or RCD protection. However, it is very reassuring when you look inside the AFDD and see that all those components still remain. You can see the bimetallic strip here and the electromagnetic coil that takes care of the overcurrent protection, and then the current transformer that helps when using an RCD for additional protection. So that helps us to understand that when installing a single module AFDD, it's not just providing protection against arc faults, it's also providing overcurrent and RCD protection. However, even with all of this, there is also one more type of protection provided by an AFDD, and that is overvoltage. If the AFDD sees a voltage over 275 volts, it will again disconnect the circuit. So this leads some to the natural question, does that mean if the AFDD provides overvoltage protection, I don't need to install a surge protection device? Well, a surge protection device, or SPD, is designed to deal with intense but incredibly brief spikes in the supply voltage. These can be caused by many things. Depending on many different factors, these spikes can happen relatively often or hardly ever. But a surge protection device is designed to kind of cushion the blow of these spikes while keeping the electrical system active and operating safely. You'll probably have noticed on an SPD there's no reset button because it doesn't trip. The device just works away until it eventually needs replacing. When the AFDD sees a greater than 275 volts fault, it will actually trip and disconnect the circuit in order to protect the delicate electronics inside itself, not the attached circuit. They also differ in another important way, which is that prolonged overvoltage on an SPD will reduce its working life. A typical spec for an SPD is to withstand 335 volts for 5 seconds, and after that the SPD will need replacing. AFDDs disconnect the supply so the potential damage only lasts a short time, and they are designed to have a slight delay so they won't respond in under 3 seconds, but no later than 10 seconds. And as the overvoltage gets higher, the time taken to operate gets quicker. So for example, at a spike of 400 volts, the device will trip in between 0.1 and 0.2 seconds. So AFDDs and SPDs are looking for different forms of overvoltage fault and protecting different things. Therefore, using an AFDD and an SPD in conjunction with each other offers the correct form of protection in line with the regs for certain circuits. And the final clever thing that an AFDD does is it will test itself periodically to make sure that it's working properly. When it's initially energized, it will perform a series of internal checks to make sure everything's operating correctly, and then it will continue to self-test every hour thereafter to confirm that it's still working. If it finds something wrong with its own internal processes, it will then disconnect itself from the circuit. Obviously, with so much going on internally, there are a number of reasons why an AFDD may operate and switch off the circuit it's supplying, and to help the homeowner and electrician know what's going on inside, they feature an LED indicator to show what's going on. Now, this may vary slightly from manufacturer, and it's common for them to include a sticker or label to show what the different LED states mean. We're going to use this Lewden AFDD as an example of how the LED communicates what its internal status is. If the LED is constantly lit, then it means the AFDD is healthy and doing its job. If the AFDD has operated and is then re-energized, it will flash a different sequence to indicate what caused it to trip. 1 flash per second for 10 seconds indicates that either a series or parallel arc fault has occurred. If it's flashing twice a second for 10 seconds, then that means that the device has experienced an overvoltage of more than 275 volts. So, having learned about AFDDs and what they will and won't protect against, we need to consider what BS7671 says about AFDD use in installations. 421.1.7 arc fault detection devices conforming to BSEN 62606 shall be provided for single-phase AC final circuits supplying socket outlets with a rated current not exceeding 32 amps in higher risk residential buildings, houses of multiple occupation, purpose-built student accommodation, care homes. So notice there the word shall was used. So in all these places mentioned there, you have to install AFDDs on circuits supplying sockets with a rating of up to and including 32 amps. There's no exceptions mentioned here at all. And just in case you're wondering what a higher risk residential building is, there's a definition there in note 1 which reads: higher risk residential buildings are assumed to be residential buildings over 18 metres in height or in excess of 6 stories, whichever is met first. It is anticipated that in many areas, higher risk residential buildings will be defined in legislation, which can be subject to change over time, as well as in risk management procedures adopted by fire and rescue services. Current legislation should be applied. As that points out, the definition of HRRBs is laid out in legislation and can change over time. It's worth noting that residential in this context doesn't just refer to where people live or sleep, but also includes areas where people may reside during the day for work. So office blocks could be included under these circumstances as well. Local planning offices should be consulted if in doubt. So what about other installations that fall outside the 4 bullet points there? Well, the regulation continues. For all of the premises, the use of AFDDs conforming to BSEN 62606 is recommended for single-phase AC final circuits supplying socket outlets not exceeding 32 amps. So, similar circuits. Their use is recommended for socket circuits up to and including 32 amps in rating. But the key to understanding this part of the regulation is in that word recommended. What does that mean? Does it mean it'd be nice to do it, but it's up to you if you install them or not? Well, BS7671 states that recommended, as used in the regs, means should, or more specifically, it's an expression in the content of a document conveying that among several possibilities, one is recommended as particularly suitable without mentioning or excluding others. So this indicates that if you want to comply with BS7671, then a recommendation isn't something that you can just ignore. You have to take some kind of measure to address the situation. It doesn't have to be the one in the regulation, but that is the one the authors of the regs have selected as the best one. So you don't necessarily have to install AFDDs to protect against arc faults, but you have to do something about them. You can't do nothing. So there we go. We've considered what an AFDD protects against, how they work, and what's inside of them, as well as what BS7671 says about AFDDs and where they need to be installed. We hope that information was helpful to you, and once again, if you'd now like to complete the training package by answering a few multiple choice questions, then please click the link in the description below, and do please check out the rest of our free training packages on the know-how page of our website eFIXX.co.uk. All that remains in this video is to say thank you very much for watching.